Hello, thank you for watching this video. My name is Pedro Zufiria and I'm a professor at the Universidad Politécnica de Madrid, UPM in Spain. This work has been developed by Carlos García Mauriño with the help of Alejandro Jarabo, Peñas and myself at the School of Telecommunications Engineering within the Cabify chair. Both the UPM and Cabify are strongly committed to sustainable mobility and to reducing the carbon footprint in cities. And within such framework, we are characterizing the public transport system in the region of Madrid. Precisely in this work, we analyze the behavior of several intercity bus lines in this region. The title of the work is Bus Pastime Estimation based on efficient data gathering from a slow mobility server. And the contents to be addressed are the following. We are going to begin with an introduction in which, besides motivating the work, we are presenting the available resources and the objectives set for this work. In the next point, we are going to explain how to maximize the amount of information gathered from a constrained API server. In this third item, we will describe the data gathering automation scripts that have been developed in this work. Next, we are going to propose an estimation scheme of the passing time which makes use of the available expected times of arrival provided by the API. Finally, we will finish with some conclusions and the acknowledgement. Let me start then with some motivation. Public transport is a very efficient way for people to move around in cities, and it's very relevant for reducing carbon emissions related to transportation. In the community of Madrid, on a working day, more than 5 million trips are made using public transport. Therefore, more accurate estimations of the time of arrival will definitely improve user experience. Let me now give the floor to Carlos to continue with this presentation.
Hi, I'm Carlos García Mauriño, a student at Universidad Politécnica de Madrid, and I have a scholarship at Cátedra Cabify, the Cabify chair. Let's go, we can go on with the presentation. Okay, let's have a look at the resources. From the Madrid Public Transport Commission, that we'll refer to as CRTM, we have an application programming interface, an API, that provides us with real-time data about the buses. The queries are made to a particular stop, and then, in that stop, for the next 3 vehicles of each line that goes through that stop, we get date and time of the estimation. This is when the estimation was made. The estimated time of arrival, or ETA, of that vehicle to the stop we are querying. And then we get a bus trip identifier that is really useful for distinguishing between consecutive vehicles of the same line. And the destination stop. But the main constraint is the server capacity. Our objectives are mainly two: efficient data collection and pastime estimation. In efficient data collection, we want to maximize the amount of information gathered from the API server. And then, with that collected data, we want to estimate the real bus passing time only from the collected estimated time of arrivals. In previous works, we see that the most common scenarios use automatic vehicle location data, and they rely on quantities that are based on real bus pastime data, for example, historic passing times. And we see that this information is indispensable for designing improved estimators that can predict the estimated time of arrival using statistical or learning schemes. Now let's go with the first part, optimal data gathering. Here, as we said before, we want to maximize the amount of information gathered from the API server. The constraint is that the server has a really limited capacity and we must avoid the saturation. So the decision variables that we have are, in this case, the number of selected stops. That is going to be how many stops are we monitoring, the sampling frequency for that polling of the stops information, the request timeout, and the number of parallel connections. First, we model the server capacity to have an approach or a first estimation of, for example, how many stops are we going to be able to monitor. We see that the average response time is 15.7 seconds when using 100 concurrent threads. With this estimation, we could say that we'll be able to monitor up to 360 different stops if the frequency is polling every minute. To see this more in detail, we'll have a look at some figures. For example, in figure number 1, we see in the horizontal axis the response time in seconds, and this is a histogram. In the vertical axis, we see the number of requests that were returned within this amount of time. And the color legend, we see that in blue, we plot the two HTTP 200 code that are the successful requests. Here we can see it mostly in the lower response times. Then in orange, we plot the 500 requests that are the ones that had an internal server error of the API server. These requests don't give us any information, so we are not interested in those. And sometimes it happens if the server is saturated, or they tend to happen more as time goes by. And then in green, we see the timeouts. Since we try different values of timeouts, we see spikes in several places. But what we get from this figure is that, as you can see, from 60 seconds on, it doesn't make sense to keep waiting for the request, since the chances of getting a 200 OK response, that is the only one that provides us with information, are really low. So reasonable values of the timeout could be, for example, 40, 50, or 60 seconds. Here, in figure number 2, with this figure we want to answer another question. That is there a correlation between the number of different lines that go through a stop and the mean response time in that stop? So here in the horizontal axis, we are seeing the number of different lines that go through every stop. And here on the vertical one, we see the mean response time in seconds. If there was important positive correlation, we would see that higher average response time values would be around here, where stops have more different lines going through them. But the correlation, as we can see, is not significant. For example, the mean response time for a stop with 50 different lines going through it, it's really similar to ones with 1, 2, 3 lines. Okay, and here in figure number 3, we see the result of testing different polling parameters. Let's have a look at the axes first. In the horizontal axis, on the horizontal axis, we are plotting the date where the samples were collected. And on the left vertical one, we are seeing the number of answers received that time, and on the right one, the number of stops that were being polled. Let's start with this. The number of stops being polled are represented with the purple line. This is the maximum amount of responses that we can get. So since we are polling this number of stops, as much we'll get this number of requests. But the requests are organized, added up, in 30-minute periods. That's why the magnitude doesn't match. But what we see in the number of answers, we should interpret this as a histogram, but the bars from a histogram would make this graph less clear. So let's have a look at the left axis now. In blue, we plot the 200 OK responses. Those are the ones that provide us information, the ones we want to maximize per time unit. Then in orange, the 500, the internal server error, doesn't give us any information. And then in green, the timeouts. A lot of timeouts are going to happen if we are polling the server with a lot of concurrent threads. And the timeouts also don't give us any information. This means the server couldn't answer before the timeout time was reached, so we get no response, basically. So what we see here at first, from polling a lot of different stops, we get more or less half of the responses with a 200 OK response. Here, incrementing the number of concurrent threads, instead of getting more information, we get less, because the server was being saturated. And then what we can see is that reducing the number of stops being monitored, the number of timeouts drops, but we don't get more information about those stops in total. But then, reducing the number of concurrent threads, the ratio of OK answers really rises. And here, in the end, we can see that we almost get a ratio of 1 of correct answers. To see more clearly the effect of the number of parallel connections, we performed a random test that is explained in detail in the document. So here in the horizontal axis, in figure number 4, we see the number of parallel connections that are being used during the experiment. On the left vertical axis, we see the number of 200 OK answers. And on the right, we see the mean response time in seconds. The left axis is represented with the blue line, and the right one with the orange one. So, what do we see here? One could think that the more parallel connections we make, the more information that we'll get. But this isn't necessarily true. In this case, we see that from 100 or 110 connections on, we begin saturating the server, and we start dropping the number of OK answers that we get. So we are using more resources, we are saturating the server, and we are getting less OK answers that are the ones we are interested in. So from this figure, we get that the number of parallel connections has to be lower than 100. Finally, we present this as a summary of this section, which were the parameters that we chose. We chose 285 different stops that were basically all of the stops in one area. The request timeout time was set to 60, as explained in a figure before, and the sampling period was also set to 60. This way, the polling system is working all the time, continuously. Whenever one polling iteration finishes, the next one begins. And the maximum number of parallel connection was set to 25. This guarantees that we are not saturating the server, and we get as much information as possible. So now we'll have a look at CRTMPoll. CRTMPoll is a Python package that was made to automate the data gathering process. The main features are: it can get the estimated time of arrivals for a given stop. It can run as a daemon. This means it can be left unattended, collecting the data for us. And it can perform a test to find out the optimal number of parallel connections, attending at the saturation and the ratio of right responses. Okay, now we have the data gathering sorted out. Let's get to estimating passing time from the ETAs. Okay, let's have a look at the assumptions. Our assumptions are that the ETAs that we get from the API are based on geolocated information about the buses. They are not random and they are not past values. They come from real-time data from the bus's mobility. And then, from that, we also want to assume that when there is a small enough remaining time, the provided estimated time of arrival matches, corresponds, or it's close enough to the real arrival time. This is because estimating when a bus is going to arrive to a stop is difficult when the bus is far from it. But if you have geolocated information about the bus and you see that it's 1 meter away from the stop, even if you have a 20% error, that error is not going to be significant when looking at the arrival time, since there isn't much to estimate. You know that the bus is at the stop. Now, let's have a look at the system setup. The main tools that were used for data analysis and processing were Jupyter, Python, Pandas, Modin, Plotly Express, Dash, and PostgreSQL. Now, we get to a new problem. There are some values provided by the API that don't come from real-time data, that are static values with the time. We'll have a look at this more in detail in the figures, but for now, what you need to know is that we classify these static estimations and filter them. Let's explain it with this figure. In figure number 5, we see the sample collection time on the horizontal axis and the provided estimated time of arrival on the vertical one. And the colors represent if the estimation is static, that is represented in red, or if it isn't, in green. Here we can see that at first the estimated time of arrival doesn't vary with time. These are different queries that were made 1 minute after the previous one, every minute, but the provided estimated time of arrival doesn't change. And then from here on, we see that it does vary a bit with time. So why does that happen? Why does this happen? Thing is, in particular in this trip that we are looking at, the bus left from the initial stop at 10 to 5 here. And then once the bus is on its way, once the bus started the trip, we get real-time data about its position, and then the API information, the API provided estimated time of arrival varies accordingly. But at first, we only get a static value, that is a prediction. We don't know how is it based, probably on past values or something, but it's not from real time, and it doesn't come from the estimation made from knowing the position of the bus. And here, in another example, we see that even if the bus is on its way, like the trip has started already, we see some variability in the data here, at some point in the middle of the trip, we start getting again these static estimated time of arrival values. This is probably because the bus lost connectivity or lost position, and this static estimated time of arrival value is some kind of a fallback value. Whenever there isn't real-time data about the bus position, they use this static value for the estimated time of arrival. With the design algorithms, we are able to classify the estimations and delete the static ones for obtaining the past time. So, how do we get the past time? As we more or less explained before, we get as the pass time the last ETA sample that isn't static, that has been filtered out, only we count the green ones here, and we get it only if the remaining time, so the estimated time of arrival minus the estimation time, is smaller than 1 minute. This is because, as we explained before, if the bus is really close to the stop, the error on the estimated time of arrival is low enough. Even if the error has a high percentage, since the magnitude of the time you have to estimate is so small, it isn't important for us. So we get the last estimated time of arrival if it was made 1 minute before, if it estimates that the bus is going to arrive in 1 minute or less. And then we get that estimation as the bus pass time. Conclusions. We see that the efficient tuning and automation of the data acquisition is crucial in data server scenarios. The developed methods provide a solution for efficient data gathering from unfortunately common slow systems. Now, with the CRTM Python package, we have already adapted it for other cities. And the developed methods allow for mobility research and the design of new solutions, providing or allowing to get past time data when only estimated time of arrivals are provided. As future lines of research, we see that the estimation of bus real passing time is crucial for future mobility characterization of buses. And the estimation of passing time is essential for the design of alternative arrival estimators based on supervised learning schemes, since we need past data for designing them. And these alternative estimators could potentially improve the efficiency of the actual ones. Acknowledgement. The authors want to thank the help and support from the other researchers and persons responsible of the Cátedra Cabify chair at the ETSI Telecomunicación of the Universidad Politécnica de Madrid. Thank you for your attention. If you have any questions, feel free to email us. Here we leave our contact details. Thank you very much.